Okay, so this was last week's homework. Okay, guys, remember now last week's homework. Okay, so we have been talking about this exothermic and endothermic reactions. Do you remember? Yes, do you at least remember what's exothermic, endothermic reactions, the differences?
Yes.
Yes, okay, now let's look at this. Hold on. All right. The fuel natural gas is mostly methane. The combustion of oxygen is exothermic. All right. I don't know why it keeps disappearing. Okay. The combustion is exothermic. Okay, so this is the equation of methane burning in oxygen to produce carbon dioxide and water. Explain why this reaction is exothermic in terms of bond breaking and bond making. So what happens is in any reaction for the reactant, first you break bonds, right? And when you break bonds, do you absorb or release heat? Do you remember? Sorry? No, breaking bonds is absorb. First, you absorb heat. So this front part is absorb heat, and then it becomes the product. When it becomes the product, it forms bonds. When it forms bonds, it releases heat. Okay, Ken? So breaking bonds, because there is a bond, what? In order to break this bond, this molecule must absorb the heat, then only the bond can be broken. All right. So in any reaction, there is heat absorbed and there is heat release. Okay, in any reaction, there is heat absorbed and there is heat release. The difference is when it's an exothermic reaction. For an exothermic reaction, this one is more. For an endothermic reaction, this one is more. Can you see the difference? Okay, so for an exothermic reaction, more heat is released. For an endothermic reaction, more heat is absorbed. So you just have to be able to explain that. Okay, so explain why this reaction is exothermic in terms of bond breaking and bond making. So you have to write the whole sentence. Okay, so more heat is released to form bonds. Less heat absorbed to break bonds. Okay, so this is the standard answer. When they ask you, is it exothermic? This is your standard answer. More heat is released. More heat is released to form bonds. Less heat is absorbed to break bonds. When they ask you endothermic, the answer is just terbalik. Okay. Did you get that?
Yeah.
Yes, huh? Okay, we only have 2 more classes, okay? We only have 2 more classes and then it's holiday already. Do you all know that?
No, I didn't know.
It's sent to you already. Your last class is the same ending as your school holidays. Okay, so just check, all right? I think few weeks ago already sent to you. Okay, so never mind. So do you understand this part? Can I answer this? The answer for A. Question B, copy and complete the energy level diagram for the reaction indicating, you must indicate the overall energy change, the energy needed to break bonds, and the energy given up by new bonds forming. So this reaction is exothermic, right? So what happens is, here is the energy needed to break bonds. You absorb first. You absorb first, okay? And then you release. Here's the product. The product is carbon dioxide and water. You release the energy given up is C. Okay, so this much is absorbed, this much is released. So how much is the overall energy change? Overall energy change is only from here to here. Sorry. The overall energy change is only from here to here. Only here is the overall energy change. Okay, you absorb, it's like you earn money, then you spend money. So the money that you have, it's like accounting lah, positive or negative. So it's only this much. That's the difference. Okay, can you understand?
Can.
Yeah. Can I? Any questions? Okay. Matthew, do you understand? You don't understand, huh? Okay.
Christina, sorry, can you explain?
Sorry, what do you say? Gahi, can you repeat that?
Can you explain again?
This part, all right, so this shows how much energy is absorbed. Okay, so this is an exothermic reaction, right? So exothermic reaction, we already counted a few times. If this one is if this one is 100 kilojoules and this one is 900 kilojoules, let's say, how do we know it's exothermic? We always take the front minus the back. So when we take the front minus the back, we can straight away know it's negative 800. Once we see it's negative 800, that means it's exo, right? Now, that's how we know it's exo. That means this one is more than this, okay? So how do we put it in the energy level diagram? It absorbed 100, but it released 900. So the difference is 800. This is the energy, overall energy change over here. Can?
Yeah.
Can I? Okay. Methane will not burn in air until a spark. Why? Okay. Can things suddenly just burn by itself? Like your methane gas is in your cooking gas. The cooking gas in your house. Okay, I'm sure everybody's house got cooking gas. Shell la, Petronas la, whatever. So this cooking gas is made from methane. It's very flammable, but will it just explode like that and burn, or must you have a stove?
Stove.
You must have a stove. And then what must you do to that stove?
Got fire.
Got fire, because it has a spark. So what happens is it starts a spark. The spark is the energy to absorb. It needs to absorb a little bit of energy first. Then when it starts to burn, then the reaction will just continue by itself. Okay, so you need to absorb energy first to break bonds, then only the reaction will occur. Will things just explode magically? Will anything, even if it's very, very super flammable, does it just explode magically, or do you need to always put a spark? Even if the whole house is full of gas, right? You need somebody to light a cigarette before it can explode, right or not? Okay, so why do you need to have a spark first? Why you need to have this thing to start the engine or start whatever first? Is because energy must be absorbed first. Okay, energy absorbed to break bonds first. So you must have energy to break bonds first. If not, no reaction can occur. Okay? All right. When 1 mole of methane burns in oxygen, the energy change is negative 890. What does the negative sign tell you? That it's exothermic. Which word describes the reaction? Oh, okay, exothermic is here. Okay, what does the negative? Heat is released. So what word describes the reaction? Exothermic reaction. How much energy is given up when 1 gram of methane burns? Okay, this question. When I have 1 mole of methane, it is 890 kilojoules. Now I'm asking you 1 gram of methane. How much energy? So you find how many moles. So 1 gram of methane is mass over molar mass. 1 gram is the mass. Molar mass, carbon is 12, hydrogen is 1 times 4 because it's CH4, so it's 16. Okay, so if 1 mole is 890, 1 gram is 1 over 16 mole. So the heat release is 1 over 16 times 890. So 55.625 kilojoule. Okay, so the energy level, the energy change represents how much energy is in 1 mole. So all you need to do is change it to, change the grams to mole, and then you can find the answer. Okay, you get it? We did a similar question last week, right? I think. A very similar questions like this we did last week. Okay, ready? Okay, what is hydrogen fuel cell? Do you remember? Hydrogen fuel cell uses hydrogen as the source of energy. Okay, we use hydrogen as the source of energy. All right, a fuel cell produces electrical energy by the oxidation of a fuel by oxygen. The fuel can usually be hydrogen, but methane and methanol can also be used. Okay, the diagram is given below. So we use hydrogen as the fuel. We force the hydrogen to release electron, oxygen gain electron, and it produces water. Okay, so basically overall, I think I know I did this with you last week. When we burn hydrogen and oxygen, you get water and you release a lot of heat. Okay, you release a lot of heat. When the fuel is hydrogen, but the product is very clean, it's only water, so it's a very clean fuel. When the fuel is hydrogen, the only product is water. What additional product will be formed if methane is used? If methane is burned, what do you get? You get water, but you also get carbon dioxide, because carbon oxidized, you get carbon dioxide. Okay, write the chemical equation that takes place in a hydrogen fuel cell. So you just put this on here. All right. At which electrode does oxidation occur? Okay, oxidation, we did this before in electrolysis. Oxidation is release electron. So anode releases electron. Ionic equation for the reaction at this electrode. So anode, hydrogen releases electron. Okay. Fuel cells are used to propel cars. Two advantages of fuel cell over gasoline fuel engine. So the advantages is no pollution, and it's actually renewable. Because gasoline is a fossil fuel, eventually you will run out. But can you run out of hydrogen? No, because hydrogen reacts to form water. Water can break again to form hydrogen. Okay, do you understand?
Yeah.
Yes,
Yes.
Okay. Ready? All right. Can I go to the next part? Anybody has a problem with the first two questions? No? Ihua, okay?
Okay.
I'm okay.
All right. Dahe, okay?
Yeah.
Ziyu, can understand Ziyu? Yes? Okay. All right. Okay, let's continue. Okay, today, okay, so these few chapters that we're talking about. So the previous class, we talked about rate of reaction. Okay, so all these three chapters we learned together because they're all connected to each other. Okay, so the previous class, we talked about rate of reaction, right? Okay, what are the factors that affect the rate of reaction? Jordan, what are the factors? Can you tell me what?
Temperature,
Temperature, okay. Gahi, one more?
Size of particles.
Particle size, okay. Ihua?
Concentration.
Concentration. Okay, and then what else? Ziyu, can you tell me one? Temperature, particle size, concentration. Light intensity, yeah. Light intensity is the special one. It's only for reactions that are photochemical reaction. Okay, so only photochemical. Some more? Jordan? Anything else? Pressure, and one more, catalyst. Okay, so these are the 5 factors that affect rate. Okay, so these are the 5 factors that affect rate. So we talked about this a lot. So our first chapter was rate. Okay, rate meaning whether a reaction is fast or slow. Okay, that was rate. And then we talked about thermochemistry. Okay, then we talked about thermochemistry. Then thermochemistry is whether it is endo or exo. Right or not? That's what we just did only by counting the energy change. It's either exothermic or endothermic. Exothermic means the temperature goes up. Endothermic means the temperature goes down, correct? Okay, so if a chemical reaction, okay, I want you to think, if a particular chemical reaction is exothermic, okay, if a particular chemical reaction is exothermic, will the reaction happen faster or slower?
fast.
Faster. That's why explosions that are exothermic, because all explosions, all combustion are exothermic. That's why explosions are so dangerous. They burn, they release heat. The heat that they release make the rate of reaction higher. Can you see the connection now? If it's exothermic, it releases heat. When the temperature is higher, it makes the rate higher. So the reaction occurs even faster. That's why it's called an explosion. Explosion doesn't magically become an explosion, you know. Explosion actually, if you do slow motion, wait, let me try and find a video slow motion. Okay, so we talked about rate and we talked about thermochemistry. So if it's an endothermic reaction, then the reaction becomes slower and slower lah. Correct or not? Because it already absorbs heat, so the temperature will go down and then the rate will go down. So it's actually connected to each other. Now, in your IG, you have to learn to connect everything together. Okay, so there's one more reaction that we're going to learn today, which I showed you a short video just now while waiting for our friends. It's called a reversible reaction. Okay, so now we're going to go through the three things that are connected to each other. The first one is rate. The second one is thermochemistry. And now we're going to talk about the third one, which is equilibrium. Equilibrium also means a reversible reaction. It's also talking about a reversible reaction. Okay, so these three things. So today we're going to talk about number 3. Okay. Now, certain reactions are reversible. What does it mean, reversible? Okay, so certain reactions are non-reversible. An example of non-reversible is frying an egg. Okay, you have an egg, you break it, you fry it. Can you unfry an egg? Can you unfry an egg? Can you make the egg back into egg yolk, egg white, and then put back inside the shell? Can or cannot?
No, but
No.
if that happens, that's great.
Yeah, if it happens, it's really, really cool. But unfortunately, we got no rewind button, cannot. Okay, you cannot unfry an egg, so cannot. So this reaction is non-reversible. So this is like, teacher, you're so funny, you talk about this. Of course cannot lah. Okay, so this one cannot. Let's talk about something else. Burning. Okay, burning. You take a piece of charcoal, coal, carbon. You burn with oxygen, it produces carbon dioxide. This one burn, carbon dioxide go and then left nothing. Can you unburn it? Can you go and catch the carbon dioxide in the air and split it up to carbon and oxygen again and make back your piece of coal? Can or cannot? What do you think? Yes, no?
I think no.
Of course not, cannot. Combustion is one way. You cannot go and take the carbon dioxide in the air. If people can do this, we all will be the richest people in the world, because it means that fuel is reversible. So when you burn petrol, can you go and remake the petrol? That'll be fun. So no, cannot. Okay, so burning is non-reversible, but certain reactions are reversible. Name me an example of a reversible reaction. So you all understand non-reversible, Okay, so a reversible reaction. Reversible reaction is something that can go both ways. Okay. So a reaction where the reactant and product can react. So for example, ice melt to become water. Is this reversible?
Yes.
Yes. Can water freeze to become ice? Of course can. Okay. So this is a reversible reaction. How do we write it in chemistry? Water Can you please write this down? In liquid form, the arrow is like this and then becomes, sorry, it's not ice. I started with ice. Ice is solid. Becomes water in liquid form. This is reversible. Okay, can you write this down? So this arrow represents reversible. Where the reactant, sorry, the product can change back to the reactant. Okay, the product can change back to the reactant. Okay, so I'm going to show you the video again. Okay, I'm going to show you the video again, and then I'm going to explain to you about it. Okay, so give me a minute, yeah. So it was talking about endothermic and exothermic, right? In a reversible reaction. Okay, so what does it mean? So let me show you. Okay. Okay. Now, if we are talking about water, okay? If we're talking about water, we just talk about this reaction, okay? We just talk about this reaction. When I want to change ice to water, do I heat it up or do I cool it down? When I want to change ice to water, does it heat up or does it cool down?
Heat up.
Heat up. So because it's heating up, is it absorbing heat or releasing heat?
Absorbing.
Absorbing heat. So because it's absorbing heat, this direction is endo or exo?
Endo.
Endo. Remember, absorb is endo. Okay, then from water to ice, it's releasing heat, right? So releasing heat is exothermic. So if the forward, so the reaction from ice to water, this arrow is called forward reaction. Okay, forward reaction. And the reaction from water to ice this way, it's called the reverse reaction or the back reaction, backward reaction. Okay, so from ice to water is called forward reaction, is endothermic. Then the reverse reaction is exothermic. Okay, let's look at something else. Okay. Hydrated copper sulfate and anhydrous copper sulfate. Actually, what is hydrated copper sulfate? I'm sure you all remember copper sulfate is supposed to be blue, right? Hello, do you remember copper sulfate is blue? We did it in electrolysis last time. Okay. Do you remember that copper sulfate is blue? Yes?
Yeah.
Yes, okay. Copper sulfate is blue because those are crystals. So the blue crystals are actually hydrated. So when you write the formula, the hydrated copper sulfate is like this, 5H2O. Now, when you touch the copper sulfate, it's not wet, okay? When you touch the copper sulfate, it's not wet, but inside the copper sulfate, the water crystals are trapped inside. So if it's endothermic, what I do is I heat it up. Okay, I heat it up. I put fire underneath it. When I heat it up, what happens is the copper sulfate absorbs the heat. So where will the water go? The water will escape lah. So when the water escapes, who is left inside? Without water. Without water is called anhydrous copper 2 sulfate. So anhydrous means without water. Okay, this word anhydrous means without water or dry. Okay, hydrated means the water crystals are trapped inside. Can you understand? Hello, can you understand or not? Can Okay, so hydrated copper 2 sulfate is blue, anhydrous copper 2 sulfate is white. Okay, so if I take the anhydrous, how do I change it back to hydrated? All I need to do is what? Add if I have the white color anhydrous copper sulfate, how can I change it back to the blue hydrated copper sulfate? What do I add?
Water.
Water. Yes, I add water. So all I need to do is add water and then it will change back. Okay, so this is the equation. Can you please write down the equation? Okay, so this is blue and this is white. Okay. Can you write down this equation? So this reaction is reversible. I can keep adding water and take out water, add water and take out water. Okay, ready? Okay, so now what happens is that if I have these two substances, one is water, one is ethanol, 100% pure ethanol. Is ethanol water?
No.
No, but does it look like water? Yes, it looks exactly like water. So if I want to test the presence of water, I want to know if water is there or not, I add it to the anhydrous copper 2 sulfate. I add water, it will turn blue. I add ethanol, there will be no change. That's how I know whether it's the presence of water. That means whether it is water or it's not water. Can you understand? Okay, so you just add it to the copper 2 sulfate. Okay, if this is just to tell me whether it is water or not water, how do I test the purity of water?
pH level.
No. Not pH level.
Boiling
Boiling
melting
point. Yes, very good. Okay, so the presence of water is anhydrous copper 2 sulfate. The purity is boiling point or melting point. So don't get the two confused. Purity means there's only water. Presence of water means it could be salt water, it could be sea water, whatever water, as long as it's got water. Okay? All right. Another thing that we can, so two things are, they ask you in IG, two things that can be used to test the presence of water. One is anhydrous copper 2 sulfate, and the other one is anhydrous copper 2 cobalt. Cobalt 2 chloride. Cobalt 2 chloride, when it's dry, it is blue. When there is water, it is pink. So this one can also be used as cobalt chloride paper. Cobalt chloride paper is blue. When you touch water, it becomes pink. Okay?
Teacher, during exam, will they tell us which one is what color?
No, of course not. You have to remember. Then I tell you for what? You have to remember, okay? So let me show you, okay? Hold on. Okay, all right, what I want you to do is, can you please try question 1? Question 1 is just a preliminary question for this chapter, all right? Okay, please do the question now. Forgot to record, sorry. So forward reaction is endothermic because you see here is a positive, so the reverse is exothermic. Okay. All right, so remember there's two reactions, okay? There is, to test for water, there's two. One is cobalt chloride. Cobalt chloride changes from blue to pink. Copper sulfate changes from white to blue. So there's two kinds of reactions to test for water. Okay? You must remember both reactions and you must remember both color change. Why so many things to remember? I don't know. Okay? All right. Okay. Can you see this next question? Okay. Okay, I'm going to explain to you about this now. All right, so this is what happens. This is what happens. In a reversible reaction. Okay, what happens in a reversible reaction? So I'm going to talk about this part now. Okay, are you guys all ready?
Okay.
Can I? Okay, so congratulations. Sit down and contemplate life. We're going down. Then go answer the phone. Close the door and go answer the phone. Okay. So let's look at this. When hydrogen reacts with iodine, it forms hydrogen iodide. Okay. Now, what happens is this reaction is reversible, but I put it in a container. I put it in a closed container. Why must it be in a closed container? It's in a closed container so that the gas doesn't escape. Okay, if the gas escape, then stupid lah, why I want to do the experiment? Everything escaped already. Okay, so I use a closed container, which is also known as a closed system. Okay, in a closed system. All right, so what I do is I only put my reactants. I only put my reactants. So here I put some hydrogen. And here I put some iodine. Okay. Hydrogen, iodine. All right. Okay, so I put some hydrogen. And I put some iodine. Okay, a lot lah, I'm not going to draw all. Okay, so what's going to happen is, first, their bonds are going to break. And then they're going to form hydrogen iodide. Okay, so at first don't have all this, right? At first don't have all this, correct? And then they start to react and then they start to form. Correct? Okay, now what happens is initially because don't have hydrogen iodide, there is only a forward reaction. Okay, initially because there's no hydrogen iodide, so there's only forward reaction. Only this way. Okay, once there is some hydrogen iodide that's formed, quite a lot of hydrogen iodide, then the hydrogen iodide says, hey, I don't feel like being hydrogen iodide. So I start out with 100 of this and 100 of this. After a couple of minutes, this one become 99 and 99 and form one of this. Okay? After another couple of minutes, this one becomes 90, 90, and then forms 10 of this. All right? After another couple of minutes, it forms even more of this. Now, up to a certain point, this hydrogen iodide says, hey, I want to change back to become hydrogen and iodine. So some of the hydrogen iodide decides to change back. It's not going to happen in such a way where all 100 of the hydrogen and iodine suddenly all disappear and all form hydrogen iodide. No, that's not going to happen because this reaction is reversible. Because this reaction is reversible, meaning that after you form this, this will break apart again to form these two. So after a few minutes, you will have a mixture. You will have a mixture of some of this, some of this, some of this. Okay. Now it doesn't go by amounts. It goes by percentage. So maybe you will have 20% of this, 20% of this, and then 60% of this, for example. Or it could be 30% of this, 30% of this, and 40% of this. Okay, we don't know what's the percentage, but basically it will reach a point where at first this one is 100%, 100%, and this one 0%. This one will start forming this, this one will start forming this, but it will not become here 0, 0, and then here 100%. No, it won't become like that because this reaction is reversible. That means this becomes this, this also change back to become this. That's what reversible means. So after a while, they will keep going forward and backward, forward and backward, forward, backward. They can't go on forever. Okay, they can't go on forever. They will go up to a point where they will say, okay, I'm happy already. This can be any percentage. Okay, it can be any percentage. It could be 25% hydrogen, 25% iodine, and 50% this. It could be this, or it could be something as funny as 10% this, 10% this, and 80% this. We don't know. We don't know what's the percentage. That, I mean, there's a way to calculate. We don't know it. but basically they will reach a certain percentage and then they will stay there. They will stay there because the amount of hydrogen and iodine becoming hydrogen iodide is the same as the hydrogen iodide becoming iodine and hydrogen. That means forward and backward reactions both happen, but they happen at the same rate. Okay, they happen at the same rate. That means hydrogen and iodine becoming hydrogen iodide and hydrogen iodide breaking to become hydrogen iodine happen at the same speed. Okay, so at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And this is your definition for equilibrium. Please write this down. This is what equilibrium means. Okay, the rate of the forward reaction is the same as the rate of the reverse reaction, and then there would be no overall change. Okay, there will be no more changes already. They will stay at 10%, 10%, 80%. For example, it could be 40, 40, and then 20%. You don't know, but they are happy already. Okay, have you all written this down? Hello, have you all written this down?
Yes.
Do you all understand what I mean?
Yep.
Okay, can understand what it means, huh? Okay, so this is what it means by equilibrium. That means the rate of the forward and the backward reactions are equal. Okay. All right, now, when a mixture of hydrogen and iodine is heated in equilibrium, hydrogen iodide is formed. Okay. So you're supposed to draw you're supposed to draw a diagram where there is more products than reactants. Okay, more products than reactants. Okay, so for example, this one, right? This one is product. Okay, this one is product. So there's more of this. Okay. So this is the equilibrium lah. So for example, this is equilibrium. Okay. Okay, I know it's a very new concept for y'all. Okay, I know it's a very new concept for y'all. Are you all okay? Do you need a 5-minute break? Everyone okay?
Yeah.
Yes, all okay. Okay, I'm going to show you a video. Okay, because I know it's a bit tiring because it's a very new concept. for today, I'm not going to okay, I gave you these questions, but I'm not going to ask you to do because this one I need to teach you all some more things. Okay, so I'm just going to teach you the theory today. I'm not going to teach you all the theory because I think your brains will explode. It's a lot of things, but I'll try and finish up this whole chapter in the next 2 weeks or so. Okay, so basically you all understand equilibrium. Equilibrium means that the rate of forward and backward reactions are equal. They are happy already. Whether it's 80%, 10%, or it's 50-50, you don't know, but they are happy. Now, in a closed container, you can shift the equilibrium. So for example, okay, now we talk about shifting the equilibrium. Okay, shifting the equilibrium. Nitrogen is a gas. Hydrogen is a gas. They react together. Okay, this one you really must copy. You must copy because if not, you won't understand. They react together to form ammonia. Okay, so this is my reactants. How many moles? Oh, not yet finished, not yet balanced. Sorry. Okay, this is my reactants. How many moles of gas do you see?
4.
4. Okay, if you cannot see 4 moles, we have other big problems. Okay, so here is 3 and here is 1. So in total, there are 4 moles of gas. Okay, over here, how many moles can you see?
2.
2 moles. If you cannot see 2 moles, we have an even bigger problem, right? So here is 4 moles, here is 2 moles. Okay, now this nitrogen, hydrogen, and ammonia have reached equilibrium. We don't know what's equilibrium. Let's say it is 25%, 25%, and 50%. Let's say, we don't know, okay? We don't know. Let's say it's 25, 25, 50. So it doesn't matter what's the equilibrium. What basically means that it has already reached an equilibrium. So you no need to bother about what the equilibrium is. It can be any percent. It can be this one 30%, 20%, 50%, doesn't matter, but it has reached an equilibrium. Okay? So if the pressure is increased, okay, this side got 4 people. This side only got 2 people. Okay, if I am increasing the pressure, I am making the space bigger or smaller.
Smaller.
Smaller. If I am making the space smaller, they will prefer to be more people, or they will prefer to be less people. Less people. Makes sense, right? So if I increase the pressure, it will follow, okay, it will favor. Favor means it will prefer. Favors the side with less moles. Okay, this chapter, there's a very specific way to write. Okay, so it favors, that means it prefers, it likes the side with less moles. So who is the one with less moles? The forward, right? Okay. So the reaction goes this way. The reaction goes this way. That means maybe just now without high pressure, it's 25, 25, and 50%. Now you increase the pressure. Now you increase the pressure. It became 70%, 15%, 15%. Can you understand? Can you understand? That means to become more of this. Okay? Guys, you understand what I'm saying?
Yeah.
Yeah. So it favors the side with less moles. So the way we write is it shifts the equilibrium to the right. It shifts the equilibrium to the right. So you can either say it shifts the equilibrium to the right. Some of you right and left not very good. Or you can say it favors the forward reaction. Okay, so it favors the forward reaction. Okay, so we can either say it shifts the equilibrium to the right, or you can say it favors the forward reaction. Okay, so because of this, will I have more reactant or more product?
Product.
More product. Okay, so I will have more of this. I will have more product. So having more product means I got more yield. The word is yield. So more product. So the yield increases. Okay, please write all of this down. Okay. Okay, do you all understand?
Yeah.
Now, what happens if I decrease the pressure? If I decrease the pressure, what will happen? Will it shift to the right or will it shift to the left? Hello?
Shift to the left.
Shift to the left because it will favor the side with more moles. So it's the same thing terbalik lah. High pressure favors less moles, low pressure favors more moles. Okay? But it must be only gas. Okay, now I'm going to show you another one. Okay, ready? Okay. Now, let's say I have hydrogen gas, iodine gas, hydrogen iodide gas. Okay, this one I put high pressure. Okay, how? Will it favor the forward or favor the backward?
Same.
Sorry?
Both also 2 moles. So
Both also 2 moles, and then
it's always in
No
equilibrium.
change.
no change. Very good. Okay, high pressure or pressure, no change. No, does not change the equilibrium. Okay, or it does not change yield. When they ask about equilibrium, they are talking about yield. It does not change the yield because both sides have same number of moles. Okay. All right. Can I understand? All right. So the first thing we learned today is shifting the equilibrium. Okay. The first thing we learn is pressure. Okay. So high pressure. So conclusion, high pressure favors less moles. Okay, favors the side with less moles. Low pressure favors the side with more moles. Okay, if both sides has same moles, then there's no change when the pressure changes. Okay, Ken? Okay, everybody?
Yeah.
Any questions?
No.
Noah? Okay.